Okay, everyone, welcome to the Mechanical Design course, Lecture 2. This is about the basic physics. It's part 1 of the physics. This is a 2-part lecture, such a large topic that I can't put it all into one lecture. So that's why I'm doing it this way in 2 parts. So basic housekeeping, just some updates for this course. I decided that there's some problems with the way we decided to do questions last time, which may or may not have caused problems. I'm not sure. But I think if you want to have questions, you want to make sure that if you don't want to say it live with your own voice, you can still ask them. So if you have any questions during the presentation, please type them in the chat and I'll just read them and I won't say your name unless you want me to. Also a disclaimer. Some of these topics are foundations for other topics that are more relevant to machine design. What I mean by this is that during this presentation, there's going to be a lot of things where like, what is happening here? Like, how is this useful for robotics? How is this useful for machine design? It's very hard to see how this works. It's just kind of math and, drawings and stuff. But hopefully, eventually, by the end of next lecture, you can see how these things can be implemented into robotics and machine design. I just want to make sure you're forewarned. So what will we cover in part 1? Displacement, velocity, and acceleration, otherwise known as kinematics. Newton's 3 laws, friction, angular motion. Part 1, displacement, velocity, and acceleration, the foundations of mechanics. Displacement. Displacement is the distance between the starting point and the ending point of motion, which is the net change in position. In this case, I use an example of moving in a circle. The reason why is that knowing the difference between distance and displacement can be somewhat difficult. But in this case, we have this yellow dot, and it moves around the circle, like around a track. Now, in this case, the distance is the dot traveling around the whole circumference of the circle. It travels around. However, its starting position and the ending position is the same. So the displacement the dot traveled is 0. That's the difference between displacement and distance. I hope you can understand this. This is a very important topic for the rest of the lecture. So why is displacement important then? Displacement is used for velocity and acceleration rather than distance. If you were here for the first lecture, you know that displacement is a vector, distance is a scalar. Now, to summarize vectors versus scalars, scalars are normal numbers. They're just a magnitude. So something that is just like this big. However, vectors are magnitude plus a direction. So you, instead of saying, like 10 miles per hour, you would say 10 miles per hour northwest for a velocity instead of speed, which is the scalar versus vector. In this case, distance requires a direction, while distance can just be any whole number. Displacement will henceforth use the variable delta x and will be measured in meters. We'll be used the symbol delta a lot during this presentation. What that means is change in. So we'll go over this later, but think about it as final position minus initial position, change in x. Next up, velocity. Velocity is displacement divided by time. We use meters per second. The equation for velocity can be written as v equals delta x divided by t. This is assuming there is a constant velocity. If there isn't a constant velocity, we'll have to use different equations. But if there's no change in velocity, it's delta x divided by t. Velocity is the speed as displacement is the distance. So like I said earlier, the velocity is the vector version of speed, which is a scalar. Displacement is the vector version of distance, which is a scalar. Some examples here will be velocity in a circle versus in a line. Like we showed earlier in the track, the displacement around a circle is 0. That means the velocity overall is 0 because you don't move at all. However, in a line, you're going in a direction and you're going, their end position and the start position is different. Therefore, velocity will not be 0. There are cases where if you're thinking about smaller positions on the circle, velocity will be greater than 0. This is only when we're looking at the start position and the end position. So if you're halfway across the circle, it will be the sorry, I forgot. It's like whatever, it'll be 2 times the radius. Can't believe I forgot that word. of the circle. So why is velocity important? Velocity is used when direction is important. For example, we want to know what direction a robot is moving as much as its speed. We care about its speed, but we also don't want it running backwards. We want to make sure that the direction and speed are both important here. Often a change in velocity is a very useful variable, just like how a change in position is displacement. In order to find this, we can use both initial velocity, or v naught, and final velocity, v. Delta v equals final velocity minus initial velocity. Like I said earlier, delta. Acceleration. Acceleration is the change in velocity divided by time, meters per second squared. The formula for this is a equals delta v divided by t. This is just the variable form. This is assuming there is uniform acceleration. Uniform acceleration means that the acceleration stays constant the entire time, so there isn't a change in acceleration. With acceleration, direction almost always matters. For example, braking and speeding up in a car are both acceleration. But we want to make sure that the direction is right, because you don't want to be thinking you're braking and actually speeding up. Once again, it's another example of it being a vector instead of a scalar. Why is acceleration important? Acceleration is caused by forces. These forces are what cause motion. In essence, we use different forms of acceleration to control motion. If you're here for part one, like I said, everything about machine design is learning how to fundamentally control motion. Some examples here are rockets. They use the thrust from their engines in order to cause acceleration so they go upwards. If we didn't have acceleration, they'll have no control over the rocket, it'll just sit there. Also for cars turning, the force of friction caused by the wheels accelerate these cars to the left. If you didn't already know this, the way cars turn is that the actual friction of the wheels turn the car. It's somewhat interesting because you don't really think about it very much. So how do these relate mathematically? There are 5 commonly used equations to relate these 3 quantities. They are called the kinematic equations. Remember that word. These depend on what variables you have data for and whether the object is accelerating or not. 1 is for an object under a constant velocity. 4 are for an object in uniform acceleration. Luckily, we already know the first one. V equals delta x divided by t. This can then be rearranged for displacement. Delta x equals v times t. This shows that if we multiply the velocity by the time, we get the total displacement. This makes sense because we get velocity by dividing displacement by time. So if you just multiply the time again, you get the displacement. The other 4 should be used when there is uniform acceleration. Like I said earlier, there is no change in acceleration. Those are delta x equals initial velocity times time plus 1/2 times acceleration times time squared. The next one is velocity squared equals initial velocity squared plus 2 times a times delta x. The next one is change in velocity equals acceleration times t. And the last one is delta x equals 1/2 times velocity plus initial velocity times time. I also put all of the variables that each equation has to the right. I'm going to stay here for a few seconds just to make sure everyone can write these down. If you have notes, I recommend writing them down. Okay. So here's an example. Our FRC robot starts at rest, then accelerates by 2 meters per second squared to the right for 5 seconds. How far is it from its original position? First, we must figure out what variable we need to find. In this case, it is displacement, or delta x. Second, we need to figure out what variables we have. In this case, we have acceleration, time, and initial velocity. Third, we need to find the equation that uses those variables. So in this case, I already found the equation, which is delta x equals v naught times t plus 1/2 at squared. This has displacement, initial velocity, time, and acceleration. Now we ought to fill into the variables to find the answer. So delta x equals 0 times 5 plus 1/2 times 2 times 5 squared. To do the math there, it works out to be 25 meters to the right. The reason I say to the right there is because it is a vector. The direction is important. However, I don't technically have to say to the right here because it is positive. In the case of vectors, numbers being positive or negative actually indicate what direction it is going in. So in this case, if we assume that right is the positive direction, we can just say 25 meters and we assume it's to the right. But for now, I would just say the words to the right. Sometimes it will be necessary to rearrange each equation. For example, the equation v squared equals v naught squared plus 2 times a times delta x can become delta x equals v squared minus v naught squared divided by 2 times a. We do this in order to make sure that we can find any variable in the equation. So as long as the variables in that equation are the ones that are relevant to the question at hand, we can rearrange them to make sure that we get the right answer. This is why in lesson 1, I went over algebraic rearranging and manipulation, because it's so important for physics to be able to take any equation and just rearrange for any variable. So an example here is delta v equals a times t can become t equals delta v divided by a. Remember, these equations can only be used if there is uniform acceleration. If it isn't under uniform acceleration, they will be wrong, and you'll be laughed at. So don't do that. Questions?
So, the equations are just for getting delta x, delta v, and how come there's 2 equations for delta x?
2 equations for delta x?
Mhm.
So in this case, I'm going to go back to that slide. In this case, 3 equations actually have delta x. And the reason why is that there's other variables in those equations you might have or might not have. So in the first equation, you would want to have delta x, initial velocity, acceleration, and time. But the next one, you don't have to deal with time. So if you don't know the time, that one's very useful. However, you do need to know the final velocity. We might go over this later, but what's very common for this second equation is that the final velocity is 0, or the initial velocity is 0. So therefore, you only need to have 3 variables. And for the last one, we don't have acceleration. This one is in essence just taking the average velocity and dividing it by time. And under the case of uniform acceleration, that will be correct. But we have to make sure that we add both the initial and final velocity and just divide it by 2 to get the average. However, in this case, we don't need acceleration. So if we don't have acceleration, that one's good. It all depends on the circumstance.
Thank you.
Also, yes, A equals acceleration. That was on chat. Any more questions? Okay. Newton's 3 laws, an introduction to dynamics. This section is the largest section of the lecture, by the way, so just get ready for a lot of stuff. Remember forces? Forces are what cause motion, but what does it really mean when I say that? Intro to the laws. Newton's 3 laws of motion show how forces can change and control the motion of an object. Specifically, they allow us to predict it. So in this case, like I said earlier, we want to control motion. And the way we do that is with acceleration. But in order to cause acceleration, we have to cause forces. Now, we use Newton's 3 laws of motion in order to figure out the rules of how motion works with forces. How does force relate to the motion? So in this example, they can allow us to model how much force is needed to lift our robot. This is a very important question. If we're making a lift for our robot, we need to know how much force is necessary to make it so our robot moves up. Also, we have to make sure how much force is necessary to make sure the robot moves up at the correct speed. However, there is one topic we need to discuss first. Free body diagrams. If you are in physics, you would already know this, but for people that aren't, I'm going to go over them first. Free body diagrams are used to visualize the different forces acting upon an object. This is a very useful tool for understanding forces. You will use these in both physics classes and in engineering, but luckily they are pretty easy to understand. Now let's go over them. Here is the simplest example of a free body diagram. A box. You see this brown center point in the box. That is what we call the center of gravity or center of mass of the object. It's basically an infinitely small point that's in the middle of all of the mass, and it's where gravity affects an object. Don't worry about it. It's just all of the forces currently, until we get to rotation, will be coming out of this center of gravity. But for now, there are no forces acting upon this object. Therefore, it is just chilling in space. Nothing's happening to it. It could be moving, it could be not, but nothing's happening to it. Here's a slightly less simple example. We have a box with a force pointing downwards. That's what the arrow is. And we put a label of that force, F of G. This example is in what is called free fall. The only force acting upon this object is the force of gravity, F of G, otherwise known as the weight. So if you didn't know this already, the word weight is just another way to refer to the force that gravity exerts on the object. Note for later, this force is unbalanced. Remember that term. Here's the last example for now. We have two forces. This is an example of an object sitting on a surface. That's what the gray bar is. It's just a surface of the ground. There is both a force of gravity going downwards, and now we have a normal force going upwards. Now, this normal force is very important to understand what it is. Essentially, if you're standing on the ground, force of gravity is still pulling you down, but there's another force that the surface is pushing back up against it in order to make sure you don't fall into it. As long as the floor underneath you doesn't collapse, the normal force is going to be equal to the force of gravity. Note for later, this force is balanced. There are more complicated ways to use free body diagrams. We can use vector addition to either combine or break up force components. If we don't know what any of those words mean, don't worry about it. Essentially, if we have angles and stuff with the forces, we can break them up to make it so they are on the 4 cardinal directions. It just makes it easier to do the math. Also, we can show forces coming from outside of the center of gravity. We'll use this later with rotation and torque. But we have gone over enough for now. So now, finally, we can go to Newton's 3 laws. Law number 1. An object at rest remains at rest, and an object in motion remains in motion at constant speed and in a straight line unless acted on by an unbalanced force. I stole this directly from NASA's website. They write better than I do. But in more plain English, this essentially means balanced forces equals objects maintain the same velocity. Notice how I don't say objects don't move. I don't say that. And the reason why is because if an object is already moving, but there is no force acting upon it, it will stay moving. So if the velocity is 10 meters per second to the right, but there is no forces acting on that object, it will continue to be 10 meters per second to the right forever. If it's at 0 velocity, then it will be at rest forever. What does this mean visually? This is an object in space. There are no forces acting upon it. Therefore, it will keep its current velocity. Remember, it having no forces acting upon it does not mean it is at rest, like I said earlier. This is an object on a surface. The object is also maintaining its current velocity. This is because the forces are balanced. The two force vectors, if added together, would cancel each other out. In more plain words, the two arrows with the magnitude and direction, if you were to add them together, would cancel each other out because they're in opposite directions and have the same magnitude. So if you add them together, it will be 0. This is an object in free fall. This object is changing its velocity or accelerating. This is because the forces are unbalanced. There is only one force, and therefore the net force downwards is greater than 0. Don't worry about the word net force just yet. Just remember that the net force downwards is now greater than 0 because there's only one force vector, it's downwards, and nothing is canceling it out. The tendency for these objects to resist change is called inertia. This is why people sometimes refer to the first law as the law of inertia. The concept of inertia is also important for Newton's second law, as we will cover soon. Questions Okay, so I got a question in chat. Could you reiterate the part about having balanced forces doesn't mean the object is at rest? Yes. So if we go back to it having balanced forces here, what is happening here is that there is an object. We do not know its current velocity, but it has a weight downwards, and we have a surface underneath it that's causing a force upwards to make sure it doesn't fall through the surface. However, in this case, we don't have any friction. We never modeled it. And if there is an object sliding with no friction, it will keep sliding forever. Therefore, it does not mean the object is at rest. It could be at rest. If it didn't have an initial velocity, it would be at rest. But since there is no external forces because it's balanced, it is not accelerating. And therefore, if it's not currently at rest, then it will stay not at rest at the same velocity. Are there any more questions?
So assuming that we are on Earth, gravity is always constant? Or not constant, gravity is always present?
Yes, gravity is, so this is unrelated, but I will go over it. The way gravity works is that two objects are always exerting a gravitational force on each other. Doesn't matter how big or small it is. And that gravitational force goes out forever. So theoretically, there is an object infinitely far away from me that has mass, and we're both exerting a gravitational force on each other. However, the farther out you go, the weaker that gravitational force becomes. So that infinitely far away object is making an infinitely small force on me. Does that make sense?
Yes.
Okay. So when we get farther away from Earth, the force of gravity on Earth gets smaller. However, in a lot of simple physics, we will assume the force of gravity is constant on the planet just because we normally stay near the surface.
All right, thank you.
Any more questions? Okay. Newton's second law. The acceleration of an object depends on the mass of the object and the amount of force applied. Once again, stole this from NASA. The purpose of this law is to quantify inertia, or the resistance to change in motion using mass and acceleration. What do I mean by this? This is where the famous equation F equals m times a comes from. However, the F in this equation doesn't actually mean force. It means net force. Remember what I said earlier? Let's go back to the free body diagrams. This free body diagram is in free fall and has unbalanced forces. Now, what we got to know is that an unbalanced force means that there is a net force. If the forces aren't balanced, it means that there is a net force involved. Since there is only one force, the force of gravity, we know that the net force of this object is equal to the force of gravity. So to explain this simpler, think of there being a pretend arrow coming out of the object, and it is the sum of all forces coming out of that object or acting on that object. If the forces are balanced, the sum of all of the forces will be 0. However, if the forces are unbalanced, the sum is not going to be 0, and that sum is going to be the net force. In this case, there is only one force, so the sum of all the forces is equal to the force of gravity. Now, we have enough knowledge to do some math with forces. Specifically, we can now figure out the acceleration of gravity on whatever planet the object is on, only using the force of gravity and the object's mass. Let us say the force of gravity equals 100 newtons, and that the object's mass is 10 kilograms. We can use F equals m times a to find a. So currently, if we rearrange that equation, we get a equals F divided by m. And if we plug in the variables, we get a equals 100 newtons divided by 10 kilograms. So the acceleration due to gravity is 10 meters per second squared. By the way, this is very close to what it is on Earth. Good job. We just derived the formula for weight. Weight equals mass times acceleration due to gravity. With fancy variables, we say that the force of gravity equals mass times the acceleration due to gravity, or mg. Quick tip. Most of the time, it is okay to substitute mg for the force of gravity in a free body diagram. This is what we mostly do in physics. It just makes things simpler, and we already know the equation just by looking at the image. What are some other things that F equals mass times acceleration tells us? Assuming the same mass, as the net force increases, the acceleration increases. This means the net force and acceleration are directly proportional. Assuming the same net force, as the mass increases, the acceleration decreases. This means that mass and acceleration are inversely proportional. Assuming the same acceleration, as the mass increases, the net force increases. If you're confused by that, I will just play around with moving the variables in the equation to see what happens when we keep one constant and increase one and decrease the other. But if we look at those before, therefore, if we want to control motion, the three main levers we have to pull. Therefore, if we want to control motion, the three main levers we have to pull are mass, force, and acceleration. These are the three variables we use to control motion. So here's a harder example. Don't worry, it's not too hard. This is a model rocket which is taking off from the surface of Earth, in which case g equals 10 meters per second squared. The mass of the rocket is 3 kilograms, and the force from thrust, F of A, is 90 newtons. What is the acceleration of the model rocket? This is where we start summing up forces to get the net force. First, we need to sum up the forces to find the net force of the rocket. Therefore, we need to find out what mg is in order to subtract it from the thrust. The mass is 3 kilograms, and g is 10 meters per second squared. Therefore, m times g must be 30 newtons. Now, we can use that to find the net force. All we have to do is subtract 30 newtons from 90 newtons, and we get a net force of 60 newtons. With a mass of 3 kilograms and a net force of 60 newtons, we can fill out the equation F equals m times A like this. 60 newtons equals 3 kilograms times the acceleration. If we rearrange for A equals 60 newtons divided by 3 kilograms, A equals 20 meters per second. Just to get back to the person in chat, some of the later problems I will be able to let you guys solve on your own. Questions? Okay, good. Newton's third law. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. Basically, all forces require that another object to exert that force. And when that happens, the same object has the same force applied to them in the opposite direction. Personally, I think this is the hardest law to see with words. So I will use an example with free body diagrams to show it. There are two different objects with the same mass. One is pulling the other with a rope with no mass. The reason we say the rope has no mass because the rope did have mass, so it would change the equation. What we want to say is just one of the objects is exerting a force on the other object with a rope. Well, you're also assuming there is no friction. It's just important to simplify the problem. Both of these objects have a normal force and a weight, but they cancel each other out, and therefore we can ignore them from now. This is a very important thing in both physics and mathematics. If the problem at hand doesn't require us to use certain variables and they cancel out, we should cancel them out to make it easier. So in this case, since we know the normal forces and the weights are the same and they're opposite directions, we can just cancel them out. So now we just have three forces: two tension forces signaled by F of T and one applied force, F of A. Right now, the right block is being pulled forward by an unknown F of A, the applier of which is not shown. And the left block is being pulled by a tension force F of T, which is being applied by the right block. However, just as the tension force is pulling the left block to the right, the same force is also pulling the right block to the left. This is because of Newton's third law. Now, we can simplify this down even further. If we make a free body diagram of the system containing both blocks, here we will cancel out both of the tension forces, since they are equal and opposite and are inside the system. We are left with one external force, F of A. So if you are confused about what we did here, we basically pretend that both of the blocks are actually just one bigger object. Since both of the tensions are internal to that bigger object, we can ignore them. It has no effect on the actual motion of both objects, which makes sense. If you have one block being pushed and it's pulling another block with a rope, the rope's existence is not actually going to change the way that works in the long run. The force pushing one block is still the only external force. Therefore, if we wanted to find the acceleration of the blocks, we simplified a complicated problem with a ton of forces to one as simple as a freefall problem. Just one force. We can find A by taking f of A and dividing it by the mass of the system, 2m. The reason why is we have two blocks and they both have a mass of m. Therefore, A equals f of A divided by 2m. It is also important for physics to be able to relate variables without putting in numbers. So right now, we just know that the acceleration is going to be equal to the force applied divided by 2 times the mass of each. Also remember, f of A also requires another object to cause it, causing another force equal and opposite to FA on that object. So if a person is pulling the blocks and that is FA, whoever's pulling it also has a force exerted on them by the blocks. Eventually, you could simplify any system enough until there are no external forces. Honestly, in the case of reality, it's probably just the universe. But if you want to make things simple, you can think of things like the Earth or the Earth-Moon system or the solar system or the galaxy. Either way, eventually you get up to the universe, which is no external forces. Questions?
I forgot what f of A meant.
Okay, so whenever I say f of something, it just means a force. In this case, f of A equals force applied, which
Okay.
it's just give all, like, I don't know what the force is, so I'm just going to say f of A.
So like the sub, it just denotes a different force.
Yes, it's just a way to label forces. So like f of t would be a tension force, which is just a rope tension. It's just a way to differentiate them. And when we're using equations, it's also useful because they might be different.
All right, thank you.
So now we're gonna have a quick break. I'm gonna cut this out of the video. I just need a time to relax because I have a hard time with these longer presentations.
How long is this break?
Not very long.
Okay.
Okay, to go back to the questions. So we have a question. In regard to Newton's third law, what happens when an object breaks because of force applied to it? Doesn't that mean that the equal reciprocal force wasn't returned? Example, dropping a 100-pound weight on a cardboard box. It does not mean that the equal force isn't returned. It just means that when it was returning the force, it collapsed. It's kind of weird to say, but it's basically, the way this works is that when you're sending a force that breaks something. So let's say you're, in this case, on a change the example to like karate chopping a wooden block and causing it to break. What happens is that you only exert the enough force for it to break. So any force more than necessary for the wooden block to break is not given. So in this case, let's say it's 100 newtons to break a wooden block, probably a lot less than that. 100 newtons is a lot. But if it takes 100 newtons to break a block, but you would normally give off 200 newtons, you would only actually exert 100 newtons before the block breaks, and it'll stop exerting force back on you. But you would still have 100 newtons left over of potential force you could have gave them. So essentially, it does give enough back, but only enough for it to break the block. Sorry if that was a bad explanation. I had to come up with that in my head. Any more questions? Yes. So the question is, so it absorbs or cancels out up to the force that was applied? Yes, that is how it works. So it only cancels out up to the force that was applied. The force that applied has a maximum, which is how much is necessary to break the object. Part 3, friction. An application of what we have learned so far. What is friction? Friction is a force that is caused in resistance to movement when two objects slide against each other. Here's a really good example I like. So if you put your hands together and you like slap them together, you crush them. So you put a lot of force between your hands and you tried moving them. It's really, really hard to slide your hands. But if you just like lightly touch each other, it's super easy to slide your hands. That is an example of friction in action. As we can see with the rubbing hands example, the more force we exert with each hand, the higher the friction. This force is the normal force between the objects, in this case, hands. So this is another example of a normal force. The two surfaces of the hands are creating a normal force on the other hand. With this, we can see that the friction is directly proportional to the normal force. In other words, as the normal force increases, the friction now increases as well. There are also two types of friction, static and kinetic. Static friction is the force that keeps an object at rest, even if there is an applied force. For example, if you have a really heavy like box or block or table or anything, and you lightly touch it or push it, most likely it is not going to move very much, if not at all. And the reason why is the static friction. So, if you don't have friction, even if you just lightly tap a heavy table, it is going to move and it's going to keep moving forever. But since we have static friction, it does not meet the minimum amount of force necessary to start pushing the object. Therefore, it will not move. Kinetic friction is the force that occurs when an object is not at rest. For example, if a car is sliding, or I guess rolling down the road, it will be moving. In this case, we're pretending it's sliding because rolling makes things more complicated. If we just imagine a car sliding down a road, it does slow down over time. This would be due to kinetic friction. Here's a free body diagram example. The block is at rest and there is a small applied force. So this small applied force goes up and has the static friction meet the applied force. So essentially what happens is that there's a maximum amount of force that static friction will have for any given object. And if you have an amount of applied force that doesn't meet that maximum, the static friction will be equal and opposite to that applied force and cancel it out and cause there to be unbalanced forces. Therefore, there will be no net force and it will not accelerate. This is another example. This block is sliding to the right, therefore it is not at rest. So we only have the force of kinetic friction. So in this case, there is a net force. It is to the left. The normal force on top and the weight on the bottom cancel each other out, and we just have one arrow going left. So even though it's moving to the right, it is accelerating to the left, or in this case, it might be decelerating. Now, I think what is interesting here is if you increase the normal force, and you can do that by increasing the weight, this is what happens. Everything becomes bigger. So if you increase the weight, the normal force will therefore have to be higher. And if the normal force is higher, then the friction is higher. Therefore, this will slow down faster. The magnitude of static friction will be equal to the applied force until it reaches a maximum amount. Afterwards, the forces will be unbalanced and the object will accelerate. However, the magnitude of the kinetic friction will always remain constant while the object is moving, no matter how much force is applied. So if a block is sliding on the ground and it has 10 newtons of kinetic friction, it does not matter how fast that object is sliding, it will be the same amount of kinetic friction always. There are two equations important for friction. We have static friction is less than or equal to μs, which is the coefficient of static friction, times F of n, which is normal force. We also have the force of kinetic friction is equal to μk, or the coefficient of kinetic friction, times the normal force, or F of n. What are μs and μk? The coefficients of static and kinetic friction. These are special variables that relate the normal force and force of friction of any interaction. These values do not have a unit and are completely dependent on the materials of both interacting objects. They typically range from 0 to 1, but can go above 1 in extreme cases. So, for example, if you have a piece of glass and steel, the coefficient of friction for both static and kinetic will be really low, close to 0, almost no friction. But if you have like silicone and rubber, it'll be an extremely high coefficient of friction. So let us look back at the equations. The coefficients essentially tell us how much less or more difficult it is to slide an object than to lift it, because the normal force is the amount of force necessary to keep an object from going down. So if you have any more than that force, you'll be lifting the object. So if you multiply that by the coefficient of friction, we get the actual force of friction. So if it's lower than 1, that's the percentage of force needed to slide the object out of lifting it. And if it's greater than 1, it's just how much more times the amount of force necessary to lift an object do you need to slide it? So here's an example problem. Our robot needs to push a cube across the surface. The coefficients of static friction between the cube and the floor is 0.5, and the cube has a mass of 1 kilogram. What is the minimum force necessary to push the cube? In this case, G equals 10 meters per second squared. I will give you some time to solve this problem due to the request earlier. I would say like 30 seconds. Okay, this one might be a little tricky if you haven't, done these type of questions before. If you have done physics, this would be a relatively easy question, but here it goes. First, we can infer from the fact that the block is resting on a surface that the normal force must be equal in magnitude to the weight of the cube. Otherwise, it will either lift up or fall down. Therefore, F of n equals m times g. Second, we need to find the friction equation for this problem. Since the block is at rest, we want to find the amount of force needed to achieve the maximum static friction. Therefore, we can turn the equation f of s is less than or equal to mu s times f of n to f of s max is equal to mu s times f of n. Therefore, now we plug in mg for f of n. F of s max equals mu s times mg. I'll let you write that down. So if we go back to the initial problem, I hope you guys now have enough information in order to solve how much force is necessary. Okay, let's find out what the answer is. All we have to do now is plug in the values. F of s max equals 0.5 times 1 times 10, which is equal to 5 newtons. Since we want the minimum force to push the object, we can then infer that the needed force is 5 newtons to the right. There we go. Somebody got it right in chat. By the way, once again, force is a vector. Therefore, the direction is necessary as long as it's not implied by the question. Now, our robot needs to cause the cube to slide across the surface. The goal is to accurately slide the cube 5 meters. The mass is 1 kilogram, g is equal to 10 meters per second squared, and mu k is equal to 0.2. What initial velocity does the cube need to reach this position? Yes, you can post answers in chat. By the way, if you don't know how to solve this problem, I do recommend writing down these variables. So in case you do figure out how to do it and you want to do it before I tell you the answer, you can solve it then. Okay, let's get started. First, we need to figure out what acceleration the friction is causing on the cube using the friction formulas and F equals ma. Substituting variables into Fk equals mu k times Fn, similar to the last example, we can get Fk equals mu k times mg. Plugging it all in, we get F of k equals 0.2 times 1 times 10 equals 2 newtons. Let's see if that helps some of you out. I'm going to give 10 more seconds before I go on to the next slide. Now, we have to use F equals m times a in order to find out the acceleration, or in this case, deceleration, of the cube. By the way, in physics, everything's an acceleration. A deceleration is just a negative acceleration. The friction is in the negative direction, left, and therefore F equals negative 2 newtons. And in the problem, we know that m equals 1 kilogram. rearrange F equals M times A into A equals F divided by M. Plug it in. So in this case, A equals -2 divided by 1. So the acceleration is equal to -2 meters per second squared. So remember, we're trying to find the initial velocity. Here's a hint. If you remember the kinematic equations, you're going to need those. Okay, time to go to the next slide. Finally, we can plug A into one of the kinematic equations from earlier. So v squared equals v naught squared plus 2a delta x, where v, final velocity, is equal to 0. This is because these are the things we want. We have the final velocity, 0, the initial velocity, which is what we want. We have acceleration, which we just found, and displacement, which is 5 meters. So we plug them all in. V naught squared equals -2a delta x. This turns to v naught equals the square root of -2a delta x. We turn that into the square root of -2 times -2 times 5, which is equal to square root of 20. So it's 4.47 meters per second to the right. By the way, if you didn't have a calculator, I'm sorry. If you got to square root of 20, I'm not sure if anyone did, but if you did, I'm sorry. Questions?
I have a headache.
Yeah, that is fine.
Thank you. I'm planning on taking physics this year.
Yeah, I'll cut this part out of the video, but yeah, this is essentially a pre-physics like head start course. I can't talk about the very in-depth stuff. So people that have taken physics, especially AP physics, this is really easy. So if you have, like, I feel bad for you because you're kind of just sitting through a bunch of easy stuff. Yeah, I can go back a slide. But yeah, this is definitely introductory physics. But if you are taking physics next year, this is very useful. Part 4, angular motion. Displacement, velocity, and acceleration, but spinny. All the forms of motion we have covered so far are linear. Therefore, it's in like lines. But in machine design, we often have to deal with things that rotate. Every linear variable has an angular counterpart. So displacement has angular displacement, which is delta x equals delta theta. Velocity has angular velocity. So v equals omega. By the way, if you don't know these Greek terms, it's okay. Just start remembering them now. Acceleration is equal to angular acceleration. A equals alpha. The fundamentals of these remain the same, but their units differ. Angular displacement. This measures a difference in angle between two angular positions. So in this case, this circle with the arrow pointing forward is going to rotate 90 degrees. The angular displacement of this rotation is 90 degrees clockwise. Remember, it's a vector, so direction is important. For now on, we're going to use radians, which is just easier to do math with. So it'll be pi over 2 radians. If you don't know what a radian is, or you just don't know how to use them, that's okay. Just kind of go with the flow here. I recommend learning radians, though. They're very useful. So angular velocity. Omega equals delta theta divided by time, which is angular displacement divided by time. Same thing as velocity, regular, but angular. Like regular velocity, this measures the rate at which the angular displacement is changing. The unit in this case is radians per second. So instead of being meters per second, we're using the angular displacement version, which is radians per second. This measurement can be converted to a linear velocity around a curve with v equals omega times r. In this case, r is the radius. So what I mean by this, if let's say you're driving in a circle and you want to find out the velocity you have in a linear velocity you have on the edge of that circle, we can use this equation, so multiplying the angular velocity times the radius in order to find out what your linear velocity is. So for angular acceleration, alpha equals delta omega divided by time, which is angular velocity divided by time. This is the rate at which the angular velocity increases or decreases. It's just the rate at which it changes. Like angular velocity and displacement, it acts the same as its linear counterpart besides being measured in an angle instead of in distance. So here are the angular kinematic equations. Like the variables, each kinematic equation has its angular counterpart. So delta x equals v naught t plus 1/2 at squared. is equivalent to, or at least goes into, delta theta equals omega naught t plus 1/2 at squared. And for the rest, you can see for yourself. I also recommend writing these down, so I'll give you some time to do that. Okay, if you need this during questions, I can go back. So, example. There is a cylinder rolling across the ground. Due to friction, the cylinder has an angular acceleration of negative pi/4 radians per second squared. Assuming the cylinder started with an initial angular velocity of 2 pi radians per second, how long will it take for the cylinder to stop rolling? To answer a question in the chat, is this assuming constant acceleration? Yes. Okay, let's see how this is solved. First, we must find the angular kinematic equation that correlates with the variables in this problem. So we have initial angular velocity, the final angular velocity, the angular acceleration, and the time. So the equation is delta omega equals alpha times time. Next, we need to rearrange the equation to solve for time, which is what it's asking for. So if we rearrange the equation, we get t equals delta omega divided by alpha. Now, if you haven't solved it already, I'm going to let you solve it now. Okay, let's see how the numbers pan out. So we plug in the values. Remember, delta omega equals final angular velocity minus initial angular velocity. So t equals 0 minus 2 pi divided by negative pi/4. We put those together, negative 2 pi divided by negative pi/4. If you do the math there, it's 8 seconds. So it takes 8 seconds for the cylinder to stop rolling. Essentially, these are just as easy as the linear counterparts. Just make sure you understand the differences between linear and angular values. Also, don't be scared away by Greek letters. Honestly, that's probably the hardest part of it. Questions? Okay. Final thoughts. Few has been a lot. This has been almost an hour. Yeah, almost an hour long. It's been both going quicker and longer than I expected to. I think the actual slides have been quicker, but the waiting for problems to be solved has made it longer. But overall, it's been good. How do these topics relate to the course? As said in Lecture 1, the purpose of this course is to teach how to properly control motion. Physics, specifically mechanics, is the study of motion and the forces that cause it. In order for us to control motion, we need to understand its inner workings. Examples related to robotics. There are many robotics problems we can now get a grasp of with the knowledge from this lecture. One example is lifting mechanisms for a robot. We can now figure out how much force is necessary to lift a robot knowing its mass and how fast it will go after a certain amount of seconds with that force. We also know how fast to shoot a ball in order to make it travel X distance. Technically, we are going to have to derive some ideas from what we learned in this course with how, vertical direction and horizontal direction goes. But we can use all of the math we learned in this course so far in order to figure out how fast we need to shoot that ball. However, there are some topics left in order for us to solve these problems, and they'll be covered in the next part. Because the problem is that we can't just exert a force on some objects. We have some things left we need to learn, like torque and momentum, in order to show how we can truly control these forces. But wait, you have homework. Ooh, scary. Don't worry. It's not that hard and it's not mandatory. There is one section of math which is very important for solving these physics problems that we have carefully avoided so far. Trigonometry. If you do not already understand trig, I recommend that you all try to learn the basics using online resources if available. Some examples would be Khan Academy and YouTube. Without trigonometry, solving problems IRL can be difficult. The reason why is that so far we've been using forces in like 4 different directions, but it'll be really difficult if we have forces going at an angle. So if you know enough trigonometry in order to make the forces go in just those 4 directions by using the sine, cosine, tangent of those numbers, then we can solve quite a bit more equations with the same stuff we know already. So this is the conclusion of lecture 2. Any final questions?
Is it an issue if I've only been to geometry, that's my highest level of math? Will I need to
No.
learn some algebra too?
No, it is not an issue. If you want to, I'm trying to make this course easy to understand for people that don't understand a bunch of math. And there will be math that you have to look through and probably dislodge through that you might have a hard time with understanding. But hopefully the fundamental concepts you can. The reason I'm recommending this is less so for the course and more so just for being able to implement what you learned in the course and learn further from the course. Because currently this course is relatively small in time scale and we cannot learn everything there is to know. So what I want to do is give you enough information so you can now know what you do not know. Because now you can go up and like when you're seeing these like lessons and stuff and you take physics in school, you will now understand the basics of these things. So it'll be a lot easier for you to learn it. So when I
Also,
say,
continue.
yeah, so when I say you should learn algebra, you should learn trigonometry. The reason I say that is by, I would say during the summer or by the time you wish to really further delve into these topics, if you so desire, you will understand the math necessary to really go into it.
Also, will you post these presentations?
Yes, I went over this in the first lecture, but I have a week break between making the first lecture and posting it. That's just for time for me to edit, time for people to tell me, hey, I don't want that audio in the recording, stuff like that. So in this case, I'm about to post the first lecture tonight.
All
I'm
right.
probably going to post it on my own channel and then see if the AvengerRobotics channel can post it as well.
All right. Thank you.
Okay. Any other questions? Okay. All right. That wraps it up for the conclusion of lecture 2. We are done here. We don't have to slodge through physics again for another 7 days.
Yay.
For you guys watching the recorded video, I hope you had a okay time listening through this. For those of you live, I hope you have a good week.